Good afternoon, honorable judges. We are a team from HKUGA College, and today we would like to present our paper on a number of multiplicative type E and Frieze. These type E Frieze arise from finite Dinkin diagrams of type E, which are associated with cluster algebra. However, our focus is on the elementary combinatorial analysis, which we will cover later. Our study is largely based on an open conjecture suggested by Professor Fountain and Plamondon on the enumeration of E and Friezes. We will provide an explicit interpretation later as well. For our results, we achieve a full resolution on the enumeration of E6 Friezes and the unit-present QUD sequence of E7 and E8. We also propose insights for unit-free QUD sequence for the relevant types in relation to type D. Initial difficulties include high field specification with the potential employment of complex cluster algebra knowledge. Also, exceptional interdependence of variables under Diophantine constraints also increase difficulty. As mentioned, we can treat these E-Frieze as Diophantine system as shown in this example of type E4. It obeys this local Diophantine system, with the left side being a product of fixed entries and the right side being a unit entry and the product of entries based on the structure of arrows. Our aim is to study and enumerate positive integral solutions. Positive integrality is an important part for our first major theorem, which is the local global succession. The general notion goes as if two quivers satisfy the system with positive integrality. Subsequent quivers and the entire frieze can be propagated with positive integers. This is fundamental for our counting. Propagation also leads to periodicity. That means after a certain extent, the quiver will repeat itself in the system. We adopt an external classification. In this case, the period is 10. Here we give an overview of Frieze terminologies. A quiver is a specific predefined collection of entries. Notice that this extra node corresponds to the finite Dinkin diagram structure. And the QUD sequence denotes the first row across the period of the frieze. Here we visualize the Diophantine system from type E5 to E8. We also denote the quivers and the QUD sequence. Furthermore, we categorize QUD sequence into two types, namely unit-present and unit-free, as shown in the example below. Note that a QUD sequence holds unique correspondence to a frieze. Hence, we can view this problem into three key segments: finding solutions without overlapping them and enumerating all solutions. Hence, we can provide an interpretation for the original conjecture with subject to quivers and friezes. Here we have the overview of the Diophantine system. Notice that these three numbers directly correspond to the original conjecture. During our investigation, we encountered two major struggles, the first being the lack of geometric realization. Closed friezes are known to have an elegant relation with polygonal triangulations. However, similar results are yet to be unveiled for E and Friezes. Mathematicians generally believe the geometric picture is necessary for complete enumeration due to its high complexity. However, we believe it's not necessary because the algebraic structure itself is indeed within our scope of elementary investigation. For the unit-free and E3-4 enumeration case, we establish number theoretic approaches. For the cases of E3 and E4, we derive similar recurring Diophantine equations, which then by analyzing the bound of AN and DN, we yield a total of 14 and 42 quivers. For the E5 unit-free case, we derive a recurring system on a QUD sequence, which then we show there's a one maximal element for the 5-term alternating subsequence. Analyzing the upper bound of K and a case-by-case analysis yields the 5-periodic 22224 as the only possible solution. For the E6 unit-free case, we show if such sequence exists would yield a frieze with no unit entries. We then relate it to 2-Frieze, SL3 Frieze, and Grassmannian cluster category GR37. Its equivalence to type E6 concludes the necessity of unit entries in a frieze, which is a contradiction to the original statement. For the unit-present case, we propose the extended cut-and-glue operation. With a similar principle of the cut-and-glue operation of closed frieze, instead of inserting an entry between the QUD sequence, we prepend one beneath the entry of a quiver to induce a successive nature of higher EN types. We can demonstrate it by example. We'll prepare to glue one beneath this entry in an E5 frieze. Another key insight is region preservation, which ensures certain entries of the new frieze are inherited from the original one. As shown from this figure, this particular part is preserved. Hence, the remaining entries can be computed efficiently. We can yield a 7-periodic QED sequence within a type E6 frieze. The cutting operation will be its inverse, which by removing the 1 restores the original structure of type E5, as shown from this original example. The second struggle will be the vulnerability to overcounting. There are 2 main aspects to be considered. Take this E6 frieze as an example. The periodicity 7 is lower than the theoretical maximum 14. Also, E5 quivers may be independently glued, yet present in the same frieze, adding structural non-uniformity. Hence, a flexible formula is needed for effective enumeration. For the unit-free case, there is no risk of overcounting due to minimal solutions. For the unit-present case, we propose the unique QED formula. As a prerequisite to the formula, it is crucial to note that the extended cut and glue operation is performed in every entry in every QED sequence, as shown in the figure below. Hence, let's orient ourselves to this grid. The vertical axis denotes the number of pre-ordered QED sequence of type E5, and the horizontal axis denotes the position of gluing, where the 1 is prepended on the E5 QED sequence when it's glued to type E6. The number in the box shows the number of unit entries when glued to an E6 QED sequence, and the color corresponds to the periodicity after gluing. Notice that this particular region is not considered because of the periodicity of the original E5 QED sequence. For example, this one is 2 periodic, so this one should not be considered because it's gluing to the same QED sequence. The extent of removal is governed by periodicity. Hence, analyzing the count of the boxes for 7 periodic and 14 periodic cases, we yield the number of unique canonical forms. But notice that these numbers are not necessarily equal to the number of unique QED sequences. The key idea is the periodicity, and the number of unit entries must be the same if we are referring to the same frieze up to shifting. Hence, we can individually classify them to unique QED sequence with arbitrary coefficients, which we will calculate later. Taking H4 as an example, we'll take this 14 periodic sequence with 3 unit entries. This green part corresponds to a unique black box 3 in the original table. Notice that it can be glued from 3 distinct E5 QED sequence to use 3 distinct canonical forms. With this philosophy, we can enumerate H4 by simply dividing 66 by 3, yielding 22 as for the coefficient. Calculating all coefficients and summing them all together, we yield 70 unique E6 unit-present QED sequence. Applying the enumeration framework and the unit-free QED analysis, we yield the following counts for E6, 7, and 8 quivers. Notice that these inequalities correspond to the partial resolution for unit-free cases, since they currently lack complete isolation. Our paper contains a typographical error, and we are sorry about that, and the number of quivers should be 35 instead of 5. As a supplementary result, here we display the number of friezes under our enumeration framework. Side facts include the enumeration of type E5 friezes are closely related to geometry, specifically polygonal triangulations and diagonal counts. Also, the periodicity classifications under unit present condition is strict. As an example for type E7, under this particular constraint, using auxiliary open frieze, we can establish this strict 10 periodic nature. For the efficiency of our counting, we choose the most complex case of type E8. Applying the necessary operations of the unique QED formula, we found out that it can be computed by a modern CPU in less than a microsecond. As a comparative analysis with Zhang, which proposed a proof via Diophantine geometry in March 2025, coinciding with our research period, he used Diophantine geometric techniques to exhaust solutions while we derive a unified framework that ultimately unveiled the structural beauty of friezes. Hence, we believe 2 papers serve as a complementary framework, with his approach being more advanced, of ours being elementary, but the philosophical focus is we focus on the inherited structure, while we focus on a general approach with more frieze patterns to be applied. This is the end of my presentation. Thank you.